Imagine trying to draw the perfect blueprint for the human mind. Not just a program that's, smart, but a complete, unified computational theory of how we actually perceive, remember, learn, and decide. That incredibly ambitious project is the goal of what are called cognitive architectures, or CAs.
It really is the ultimate reverse engineering project. And, the reason this became so necessary, if you go back to the foundational work by pioneers like Alan Newell, is that early cognitive science, well, it was producing what he called disjoint factoids.
Factoids.
Yeah, so you'd have these isolated observations about memory over here and then something about problem solving over there, but absolutely no cohesive framework to tie it all together.
So it was fragmented, like trying to build a car by just studying a piston and a tire completely separately.
Exactly. I mean, think about fields that really succeed, like physics. It built its success on standardized, quantifiable units, the SI system, for example.
A common language.
A common language, a common basis. Psychology and early AI just lacked that, which made a unified theory of cognition seem, well, almost impossible. CAs were designed to try and impose that structure.
And that's our mission for this deep dive. We're going to explore the evolution of these computational blueprints, drawing heavily on a really comprehensive review by Katsuruba and Soltsos. We're going to see the incredible compromises and, frankly, the surprising trade-offs researchers have to make to force the mind into code, especially when you're dealing with fundamentals like sensation and memory. Okay, let's unpack that. If a cognitive architecture is a computationally implemented theory of human cognition, what did Newell say were the absolute non-negotiables, the foundations for this grand theory?
He laid out four fundamental requirements that really set the gold standard. The first two are all about scope. Number one, integration.
Yeah.
You have to combine observations about all the different cognitive parts, memory, perception, reasoning into a single holistic view. And two, unification. You have to explain a huge range of human behaviors using a minimal set of underlying mechanisms.
Be as simple and general as possible.
Precisely. You're aiming for the maximum explanatory power with the minimum number of moving parts.
So what's the thing that forces that theory into, reality?
That's requirement number three. Computability. The theory can't just be philosophical. It has to be implementable in software or hardware. This forces you to be specific, and it weeds out ideas that are just infeasible in practice.
And the last one?
The last one was fixed structure and symbol manipulation. The idea that the architecture should be stable, like hardware, and that it should operate on symbols, rule-based representations.
Right. That fixed symbolic structure feels like a hallmark of early AI. It gave us successes like the logic theorist, which could prove mathematical theorems.
It did. But that same paradigm led directly into some major historical setbacks.
The AI winters.
Exactly. The first AI winter in the late 1970s was basically a crisis of scale. It was triggered by this problem of exponential combinatorial growth in search spaces.
The Lighthill critique.
That's the one. Early symbolic methods were great in these tiny, simplified worlds.
But once they hit the messy complexity of reality,
The search tree just exploded. I mean, imagine you're searching for a move in a game. If every choice doubles the number of future possibilities, you very quickly run out of time and power to explore them all. The problem just grows exponentially.
and then about a decade later, the second AI winter hit after the collapse of the whole expert systems boom. These systems were packed with codified human knowledge, but they were so rigid.
Incredibly inflexible. Their core failing was often what's called the closed world assumption.
Meaning if a fact wasn't in its database, it must be false.
Right. It assumed that the absence of evidence is the evidence of absence. And in the real world, that's almost never true. That inflexibility plus a total lack of common sense just made them brittle and unreliable.
This whole historical cycle really seems to define the tension in the field today, doesn't it? The conflict between symbolic approaches for reasoning and then the connectionist or subsymbolic approaches for things like perception and learning.
It absolutely does. And that tension is why the most advanced modern architectures are often hybrid systems, trying to knit together the best of both worlds.
Okay, here's where it gets, for me, really interesting. Let's talk about the shocking trade-offs CAs have to make just to function, starting with how they sense the world. I mean, compared to us, they're profoundly sensory deprived.
It's true. Our analysis showed that over a third of existing cognitive architectures implement only a single sensory modality.
Just one. And I'm guessing it's usually vision.
It's usually vision, yeah, followed by somatosensation, touch, and audition. But the chemical senses, smell and taste,
Forget about it.
almost non-existent, implemented in just a handful of systems. But the simplification goes even deeper than that.
How so?
Most CAs rely on simulated sensors, or they get fully processed, pristine data. Think of the classic blocks world environment.
So the architecture never has to deal with the noise and ambiguity of real-world input.
Never. It's a clean sandbox. And that simplification, it fundamentally compromises their ability to generalize to realistic data. They're strong in theory, but often very fragile in reality.
Which brings up a critical question. If your goal is the mechanistic truth of the human mind, is it okay to sort of cheat to get the performance you want? The Kismet robot seems like a perfect example of this.
Kismet was fascinating. It could successfully categorize human utterances, approving, prohibiting, soothing.
Right.
But it did this only by analyzing the sound's prosodic contours, the intonation, the loudness, the rate. It didn't do any complex natural language processing at all.
So it achieved the function without modeling the full human mechanism. It bypassed the hard part.
Exactly. It proved you can create a really convincing social effect by just focusing on the simplest, most measurable input.
Okay, let's pivot from sensation to memory, the one cognitive ability that every single cognitive architecture has to have. And this is where the paradox is just absolute. Perfect recall is a bug.
It is the ultimate systemic failure. In symbolic systems like SOAR and ACTR, if you let knowledge accumulate forever, you eventually run into what's called the utility problem.
The system knows too much to act quickly.
That's it. Imagine a huge library that never ever gets rid of a book. Every time someone asks a question, the librarian, the system, has to check every single book, no matter how old or irrelevant.
The search time just balloons.
It slows to a crawl. And this was actually demonstrated in early tests where SOAR and ACTR they failed after solving only a few hundred simple block stacking problems.
So the overhead of finding the knowledge became greater than the value of having it. That means forgetting, which we see as a human failure, is actually a crucial engineering necessity for these things.
It's a key feature, not a bug. And it's often implemented mathematically using a decay function. In a model like ACTR, the activation of a memory decays based on its age and how often it's used.
I see. So the system is actively letting memories fade into the background, ensuring that the most valuable, frequently used knowledge is always right at its fingertips.
And that speed is critical because these CAs are modeled under very strict real-time constraints.
How strict?
Well, production systems like ACTR, UPIC, and CCAPS, they often converge on a mean cognitive cycle of about 50 milliseconds for a single decision.
50 milliseconds.
Wow, that speed is chosen to satisfy biological constraints and keep the system responsive. Any delay from memory overload would be absolutely catastrophic.
So if the architecture has optimized its memory for speed, how does it use that efficient knowledge base to actually, think and learn?
Well, it has to move beyond formal classical logic.
Yes.
Human reasoning in daily life is inherently non-monotonic.
Meaning new information can invalidate old conclusions.
Constantly. I mean, if I tell you it's raining and then a second later I see the sun is out, your first conclusion is instantly wiped out. We're always dealing with incomplete and uncertain premises.
So classic logic, which assumes everything is certain and static, just doesn't work for the real world.
Not at all. So CAs have to rely on approximate reasoning, induction, analogy, things like that to cope with all that uncertainty.
And they need to learn complex procedures really quickly. This is where those learning shortcuts come in, right? Things like explanation-based learning, or EBL.
EBL is a massive efficiency hack. Instead of resolving a problem from scratch every single time, the system just caches the results of successful attempts.
Like muscle memory for thinking.
That's a great way to put it. Think about SOAR's chunking mechanism. Once it performs a sequence of actions successfully, say, how to stack 3 blocks SOAR combines them into a single efficient macro operator, a chunk.
So the system stops deliberating on that specific task and just makes it a reflex. It goes from slow, careful thinking to fast, automatic doing.
Precisely. And ACTR has a similar process called production compilation, which fuses 2 sequential rules into one super efficient rule. They are, in essence, compiling experience into reflexes.
This whole conversation has been about perception, memory, reasoning. But a huge recent shift is the inclusion of something that was historically ignored: emotion, internal state. We're seeing behavior modulation pop up in about a third of modern CAs.
It signals a really critical realization. Intelligence isn't purely rational, it's driven by value. In us, things like pain, pleasure, hunger, They drive our choices.
Right.
So in CAs like MicroSci and SOAR, they use modulators, things like urgency, importance, or intrinsic values, to guide attention, to decide which memories to access, and ultimately to select an action.
So artificial feelings are less about a subjective experience and more about a quantifiable value system that helps prioritize what to do next.
Exactly. And it even extends to things like personality. In a system like Mehmed, you can model traits like extroversion or aggressiveness just by tweaking internal parameters, like processing speed or the capacity of certain modules. It's a mechanistic way to model behavioral variation.
Looking to the present day, it's impossible to ignore deep learning. It dominates AI. But when we talk about cognitive architectures, deep learning seems to exist in a completely separate universe. Why is there such a huge divide?
It really boils down to a fundamental mismatch in their goals.
How so?
Deep learning is focused on the functional approach. It's about scaling huge data sets and engineering artifacts that surpass human performance. They just want systems that work incredibly well.
NCAs.
They prioritize the mechanistic approach. They want to provide robust, unified, and biologically plausible explanations of how the mind works, not just that it can beat a human at chess.
And when you say biologically plausible, the big technical sticking point is usually the learning algorithm in neural nets. Backpropagation.
Right.
Why is that seen as so biologically implausible?
There are three main critiques. First, it requires identical and synchronized bidirectional connections weight symmetry. The path for the forward calculation has to perfectly mirror the path for correcting errors. There's just no biological evidence for that kind of perfect symmetry in the brain.
So the wiring it needs just doesn't seem to exist in our heads. What's the second flaw?
It's a non-local updating strategy. The change to any given connection depends on the activity of neurons far down the network. It requires information about the global activity of the whole system.
Whereas biological learning is local.
It's understood to happen locally, yeah, based on nearby neural activity. And the third major hurdle is that it requires an external control signal to switch between learning and inference.
An on-off switch for learning.
Right. Biological systems are autonomous. There's no external switch telling your brain, okay, now you're learning, okay, now you're just acting.
And beyond all those structural problems, there's just the staggering data scale disparity. Modern deep learning models consume amounts of data that no human could ever experience.
The numbers are shocking. We estimate a human might read, 2.5 billion words in a lifetime?
Something like that.
The PyleText dataset, which is used for training large language models, contains 225 billion words. That's 2 orders of magnitude more text than any person could ever see. CAs are constrained by human-scale experience, but deep learning has thrown that constraint right out the window.
We've covered a tremendous amount of ground, tracing this journey from fragmented factoids all the way to these complex computational theories. We've seen that CAs are striving for this unified mechanistic truth, even if it means making huge simplifications, simulated senses necessary for getting, and learning shortcuts like chunking.
And while these systems are getting better at individual internal functions, there's still this universal, persistent struggle. Social abilities. They consistently struggle in scenarios that involve interacting with other agents or humans. They just lack the robust perception, the complex language, the quick, flexible response needed for real social engagement.
Which brings us to our final provocative thought for you to consider. We know that true autonomy requires sophisticated interaction with others. CAs are still struggling to even define and model basic social skills and theory of mind. So given all the simplifications they've had to make, what fundamental ability is it mastering seamless, noisy, multisensory integration? Is it building a true sense of self-awareness? Or is it something else entirely? What do CAs have to solve next before they can truly interact with us as peers?
The world is waiting for that first, truly integrated artificial mind.
Thank you for joining us as we explored the blueprints of intelligence in this deep dive.